much. So yeah, I'm Anton van den Hengel. I run the Australian Centre for Visual Technologies. We are 60-something people in Adelaide in South Australia. We have 15 papers here, I think, this year. But the two that I'm most interested in are both in visual question answering. And what I thought that I'd talk about today is kind of why I'm enthusiastic about visual question answering, and particularly this bit of visual question answering that we're going into, which is about using external knowledge, right? Using a knowledge base or that sort of thing, and some of the representation questions that arise out of that, and the fact that it's heading towards being an old school AI problem and some of the implications that you might draw. So, sorry, I have to put my timer on or I'll talk all day. Okay, so vision used to be a lot closer to AI, right? And we used to do a whole lot more AI as a field. This is a picture from a paper from the 60s, I think. And you know, there was all that great stuff in the 60s where people did line labeling and constraint satisfaction and tried to turn these kind of line drawings into 3D things by these big constraint satisfaction problems. And the point of this paper was that having done that, you could then do some reasoning about whether or not that seesaw there was balanced. And this was going to be tackled analytically, right? We're going to hypothesize something about the density. Well, we're going to estimate the volume of those blocks there, assume that their density is all the same, and then figure out whether that block is going to be balanced. And it was a wonderful, some great stuff happened as part of that process. And the idea was that if we started with something simple and solved that problem, then we could slowly add complexity and just keep adding complexity until we got to problems that at the level of complexity of real-world problems. So that was a really nice idea, and there were all these predictions made. Not all of them were about vision, of course, but about AI in general. So and there's three of them there: 1965, 67, and 70. So machines will be capable within 20 years of doing any work a man can do. Within a generation, the problem of creating artificial intelligence will be substantially solved. And the best one is 1970. From 3 to 8 years, we'll have a machine with the general intelligence of an average human being. And of course, it didn't work, right? It turns out that starting with a simple idea and slowly adding complexity doesn't work as a strategy, at least in this kind of problem. Maybe there's a hell of a lot of fantastic engineering that comes from reductionism and that kind of thing, but for AI it turns out that you can't start with simple and make it more complicated. And there's been a bit of discussion about this kind of idea over the conference, right? So one of the keynotes spoke about predictions about how far away AI was. And there's a great paper on it down there where they take all of the predictions, kind of normalize them a bit. And it turns out that the prediction for how far away real AI is 20 years. And it doesn't matter when that prediction's made. It's a bit like nuclear fusion, right? Nuclear fusion is always 20 years away. And maybe it's true, right? I think that's a hypothesis that's at least worth considering. We used to think that playing chess was going to be the ultimate demonstration of intelligence. So you could read the statement as being the other way around, right? AI is what we're going to be able to do in 20 years' time. And a lot of what we can do at the moment would have been considered to be pretty intelligent if you'd looked at it 20 years ago. But the truth is that we've still got a long way to go, right? So back to the kind of hypothesis, right? Vision and artificial intelligence, I think, are intrinsically linked. There's some great theories about embodied cognition, and embodied cognition is the idea that the intelligence has to be embodied, right? If you're going to have a conversation with something that you're going to identify it as being intelligent, then that conversation is partly framed around your experience as being a human being. You know, if you meet a particularly intelligent shade of the color purple, or a gas cloud that has an amazing IQ, it's hard to imagine what your relationship is going to be, right? It's hard to imagine how that you're going to have that conversation, right? How am I going to figure out that this amazingly gifted shade of the color purple is intelligent if I have nothing to compare it with, right? You can't ask whether it's any good at crossword puzzles, or you can't even really have a conversation with it. And there was all that great work done in robotics about making COG and those projects where they were really trying to replicate human physical capabilities, and the idea that AI might thus be able to become intelligent, right, by having a human form. And humans are visual animals. If you ask people what sense they least want to lose, by and large it's their vision, and the way that we interact with the world is very visual. If you want to, so if we're going to have a robot and it's going to be of any use to you, it's probably got to have a camera attached to it, or some way of seeing in the same sort of way we do. Right? You're going to want to be able to ask your robot to go and get the blue Tupperware container out of the fridge, right? Or to, I don't know, go and find your red socks on the washing line. And that's, they're human visual references, right? If you have a robot that has a LiDAR scanner on it, it may well have a more accurate representation of the world, but if it can't tell what blue is, then it's not going to be able to find your lunch in the fridge. Yeah? And maybe you have to have both, but certainly if you're going to have a sensible conversation with a human being, you have to be able to see in the same kind of way that a human being does. So why did computer vision give up on AI? I think that and part of the kind of hypothesis of this talk is that we tend to overcorrect. Yeah, that we get too enthusiastic about things, take our eyes off the main prize, possibly overfitting is one way that it's been put, and that then we overreact as a result. So one explanation of why there's so little AI in vision is that we did the kind of seesaw thing in the beginning, right? And it didn't work. Well, it got oversold, it didn't work, and now we're overreacting to that. And that's kind of what happened to neural networks the first time round as well, right? That as a community, we got too enthusiastic about them. We overhyped it, overpromised, underdelivered, and overreacted, really. To the point where you couldn't get a neural network paper published for all those years, as some famous people have been telling us quite vociferously. And I've got some sympathy for them, right? I mean, I think they're kind of right. We did overreact. We should have been more open to it, and we should have had our eyes more firmly on the larger goal, or one of the larger goals, right? I think that it's a great triumph for vision that we've done such practical things, but we have, partly as a result, taken our eye off the bigger prize. And I'm quite fond of saying that failure is always an option. There's this thing in the entrepreneurial community now that you should fail hard and fail fast. I don't really agree with that, but I do think that we should embrace failure a bit more, or at least embrace the valiant effort, out in the right direction and failing spectacularly. I think there's a lot to be said for that. So, I think in general it's hard to imagine artificial intelligence without vision, and kind of my enthusiasm is about the fact that we're getting a bit closer. But deep learning isn't it. Again, I think are getting too enthusiastic about this idea. I think there's some really good reasons. Sorry, I don't want to stand in front of a deep vision workshop and tell you not to get enthusiastic about deep vision, but I do want to tell you that I don't think it's AI, and I don't think that it's going to get there just by getting deeper. Yeah? I think it's a critical enabler. I think it's a big missing piece of the puzzle, but that we need to use it for what it's good at and not use it for what it's not. I'm sure that everybody has a story from this conference about things being done with deep learning that really just shouldn't be. If you have an analytic solution, if you understand it, then you should do it with the analytics, right? Don't train a system. A friend of mine who should remain unnamed was approached at one of his posters, not at this conference, and part of his method was to turn scalars into something that you could represent in an image, right? Transform a scalar into pixels. And he was asked for his training data for that process, right? That's printf. That's not something that you need to train deep method for. That's printf. We have an analytic solution for that thing. The fact that you can train a method to be 97% accurate at turning scalars into pixels is not something that we should be proud of. Okay, so we need to find, as far as I'm concerned, if we're going to use this thing as an enabler, if it's going to be a part of the solution, then we've got to figure out how it's going to interact with other information and other capabilities. And that's really what the interesting bit, well, what I'm interested in this stuff at the moment, is how you can bring together this fantastic new capability and all of the other information that's out there, hopefully in order to do something that's a step towards AI, or even just a step up that ladder. And there are some other things that are going on that are fantastic, right? Memory networks, neural Turing machines. There's a couple of papers at this conference, and we're by no means the only ones looking at this issue. All right, and kind of as a result, as far as I'm concerned, the singularity is a way off yet, right? We don't have to worry about things exploding and us being taken over by the robots. As far as I'm concerned, we've got a long, long way to go. So the basis of all of this enthusiasm, in my case at least, is the connection between vision and language. And we've just seen a talk which had a lot of fantastic info about that. These communities are, I think, as Andrea said, coming together finally. But for a long time, you couldn't get a paper into a vision conference that had anything but vision in it. You couldn't get any natural language or any of that other information in. It would just lead to your paper being rejected, which I think was a bit short-sighted. A lot of those papers wound up going to the multimedia conferences and that sort of thing instead. So there are all of these, we've developed some amazing things in vision, right? We've reached the point where object detection is possible and segmentation makes sense and counting's kind of getting there. But in the meantime, natural language processing has been doing wonderful things, and I think it would be to all of our advantage if we had a better handle on some of the amazing things that have been happening in natural language processing. And even just machine translation has been a great, some wonderful work going on there. But the bit that I think is most interesting really is this question answering. And question answering has been happening in natural language processing for a very long time, right? For at least 20 years people have been talking about it. And getting great results, answering really interesting questions. And the fact that Watson won Jeopardy was a really interesting result, yeah? It didn't really seem to have as much of an impact in computer vision as it might have. Okay, but I think it's important to keep in mind that translation isn't understanding, yeah? There's the fact that that you can translate from English to French or between two other languages doesn't mean that at any point anything is actually doing any understanding, and that needs to be kept in mind as we get enthusiastic about this stuff, or as I particularly get enthusiastic about the idea that these vision to language problems might mean that we're developing a deeper image understanding approach, right? That's really what I'm interested in, is deeper image understanding. So if you if you do image understanding and language generation, then maybe you can do some image captioning. What I'm really interested in, however, is this idea that you might take all of these tools, process a question, and do some visual question answering, and that's what's coming up here. But it does bring to light this question of what's the representation, right? So if we're translating from images into language there with the image captioning problem, then there's a question about what the representation is going to be, right? Are we just going to go straight from, we're trying to is it actually even a translation problem, right? There's been this argument going on in machine translation for a while about whether you need to understand one language. You have to have this idea of understanding a model of the world to be able to do translation, right? Whether you can go from one language into a model and then into another language, or you can just go from one language straight to the other. And I think that the same issues arise here, right? So, image captioning, we've just heard a lot about image captioning, so there are some fantastic results here that got quite a lot of PR. I'll read some of the text to you because it's quite small, but the top right one is a boy doing a backflip on a wakeboard, which is actually wrong, but a really good mistake, which I think is incredibly impressive. Some of these were in Andre's talk, so you've seen some of them before. But bottom left-hand corner says, girl in pink dress is jumping in the air, which is a pretty impressive thing to be able to do with those pixels. Now, the way that stuff happens by and large, like the standard approach to that is to take an image, push it through a CNN, get a feature representation out of that, and to push that feature representation into your favorite flavor of recurrent neural network. The recurrent neural network then generates a caption. Yeah, and it generates each word in the caption in series. So, which is interesting that it works, yeah? Interesting because the first word is likely to be A or N, right? A dinner party, that sort of thing. And it's not at all clear why you should generate A or N or the as the first thing that arises out of that feature vector. Because by the time you've generated A, N, or the, you're pretty much committed to the rest of it, right? Or you're committed to some part of the rest of it. You've limited your choices, but not in any really sensible kind of way. So, but hopefully you've seen all of these things before. You've certainly seen CNNs and RNNs before. Now, this process works very well, but it's always limited to the training data. Yeah, it's always going to be, it can only ever learn from what you give it. And the truth is that the space of all images is so high, right? Or the space of all image content is so enormous, and it's combinatorial, that it's pretty unlikely that we're ever going to really be able to generate enough training data, enough pairs of images and captions, that we're ever going to be able to really train a system to do this properly, right? There are always going to be images on top of where this process doesn't work. So this is captionbot.ai. It's from Microsoft. I'm not picking on them particularly. I think it's a perfectly good image captioning process. But its guess here, in case that text is too small, what it says is, I'm not really confident, but I think this is a man standing on top of a dirt field. That's a pretty iconic image, right? That's something that most children would recognize, but this thing has no idea. This one says, I'm not really confident, but I think it's a person wearing a hat talking on a cell phone, and she seems, I guess that's, that square there, it used to be a smiley face at some point. But it does say I'm 99% sure it's Elizabeth II. She is neither wearing a hat or talking on a cell phone, but nonetheless, it kind of knows who she is. That's a good step. And again, to a big part of the population, that previous image is relatively iconic, right? This one here, to much of the CVPR audience is relatively iconic too, right? This is a very recognizable thing, but apparently the guess is it's a person sitting on the ground. And again, it's the Microsoft caption bot, but the point is really that if you're going to have a captioning process that's going to be able to caption these kinds of images, then you're going to have to do more than train it on captions. Yeah, there's just too much information out there for you to be able to, to get a full, really what you're asking it to do is get a full model of the world, right? You can take any image you like and ask it to caption it, and it's going to have to encode that somehow in the combination of a CNN and an RNN, and that's just not going to work, right? So that's kind of, that's a big build-up to this idea that going straight from an image to a sentence without anything intervening is probably a pretty hard ask. And this is the same question that people in AI have been wrangling with for a long time, which is about representations, right? How do you represent this information? And the vision, there's a lot of enthusiasm in vision for the idea that you don't need to, right? You just kind of go with this implicit representation that comes out of applying CNNs to images, and that we don't have to go any further, which I don't personally believe in. So, because what you wind up with when you run that process, right, is this right-hand set of squares here. Obviously, there are problems with trying to visualize what a CNN is actually seeing, but it's certainly some kind of implicit feature, right? It's a bunch of patterns, and it's not seeing anything higher level, right? And to go straight from a bunch of patterns like that into an RNN that's going to generate a sentence is a pretty big ask. It's amazing to me that it works at all. Our idea was, first idea was that you should add explicit high-level concepts, right? And we call these things attributes, which isn't a great name for them really, but they're attributes of the image more than, they're not attributes of the objects in the image. And attributes is a kind of loaded term. But what we really do is try to figure out what's in the image that a human would recognize, right? So a human might recognize that there are people in there, that there's a bunch of them, that they're having dinner, they're sitting at a table, there are glasses, wine, it's a party, they're talking, they're relatively happy, and that kind of thing, right? Some of them are specific nouns, some of them are more general measurements of what's going on, and the background and the scene. There's a whole lot of things that you can measure. And we particularly scraped them out of ImageNet, Coco, and the scenes information, but we've been trying to go a bit further abroad as well. And they focus the attention of the RNN on things that people care about, right? So it's an external source of information, even if you just think about the ImageNet process, right? If just the attributes from ImageNet. ImageNet have gone to a great deal of trouble the people who created ImageNet have gone to a great deal of trouble to associate that set of images with that set of nouns. There are a bunch of things that humans are interested in. They're concrete concepts. They're the kinds of things that humans care about when they look at that image. Fantastic other external information. So you're bringing in more information to this process. And it adds a lot of value. Yeah, so even at that point of just bringing these attributes in, you're adding a lot of value, right? So the way that it happens is we do the detection on the, I guess we should say we extract the attributes. So some of those attributes are whole image attributes, and some of them are detections in the image itself. So we run all of that process and generate a feature vector, which is the activations of the classifiers corresponding to each of those attributes. And then, so what you get out of that is a bunch of these attributes. That then goes into the LSTM, which does the language modeling, and that generates a much better outcome than you get if you go straight out of the image feature. And there's a bunch, you could think of a bunch of reasons that might happen, right? So this is the process, you run the CNN, but those features go into a bunch of classifiers which correspond to the attributes. Each of those classifiers is activated to a certain extent. You pass this activation vector into the LSTM, which does the sentence generation. And just doing that on its own adds a lot of accuracy. Well, it improves the accuracy of the sentence generation process significantly. And you could, there's a bunch of explanations you could come up with, and one of them, which I don't personally believe in, but one of them that has been put forward is that all you're really doing is adding another layer in the CNN, and therefore, it's deeper, and you're training it more. Well, it's just deeper, and that's enough, right? The counter argument is that if you take these activations and you go into word2vec with those activations, right? So for each one, so what's the top one there? Bag, right? Or maybe we'll pick a better one. What have we got? Well, bag will do. So you go into word2vec with bag, and you look for all of the attributes that are around bag in word2vec space, in the embedding space for word2vec, and you take that information back and you bump up the activations for all of the related words back in your attribute vector. That alone improves your sentence generation again. Right? So there's something else happening here, and my explanation for why that works is because it gets you over some of the expression problems in here. So bag. Well, so the one I usually talk about is that if you've got a couch in there, a couch will be associated in word2vec space with sleep, and bed will be associated in word2vec space with sleep. So if you get images of a couch and a question about sleeping, then it can relate those two things together, but it can also learn about images that have couches with somebody asleep on it, right? So it kind of shares the information around a bit. Anyway, I think that what's impressive about it is that it does anything at all, right? That it doesn't actually decrease performance to add this extra explicit representation, because you're kind of losing information here, right? You're gaining some of this, some information that you've got out of ImageNet and similar, but you're not passing all of the, you inevitably lose some of the CNN feature, and nonetheless it improves rather than reduces your accuracy. And that, so those attributes are pre-trained on ImageNet, and then they're fine-tuned on Cocoa, and you wind up pulling them, and but it's a pretty familiar kind of process. Now, and the bold, the bold numbers are all in the right places, right? It actually improves performance rather than making it worse. And that was on the Cocoa. So we're still talking about captioning, right? So this is MS Cocoa captions, and on all of those scores, it was the best at the time. I think there's been a couple of papers released more recently which have gone past those numbers, but at the time it was the state of the art. And exactly as Andre said, those measures are terrible. The measures that we use for these things are shocking, but nonetheless it improves on them. Okay. And some examples here. So each of these columns here is the top few attributes. Their scores, and then the black is our caption. The blue is the baseline, and the human caption is in red. So the top left one is ours is two brown bears playing on top of a lush green field. The baseline, the truth, is supposed to be a bear is walking through a grassy field, and the human caption is two bears playing in a field together, and the top attributes are brown, small, lane, plain, grass, field, and so on. Okay, so important that because adding an explicit representation of attributes of the world improves the performance of captioning. I'm more interested personally in visual question answering. There's been some great work on this area. These images come from Antol et al. The questions, in case they're too small to read, the top left, the two questions are, what colour are her eyes and what is the moustache made of? The reason I'm interested in these things is because it's you don't know what the question's going to be before you see the image, right? You're not answering just one question. The best question of any of these is, well, they both relate to the image down the bottom, right? Does it appear to be rainy is pretty good, but the best one is, does this person have 20/20 vision? Which can only be implied by seeing that that boy's got glasses on. So, in order to carry out these tasks, you've got to be able to perform all sorts of classic vision things, right? You've got to be able to do detection, counting, reconstruction. Answering general questions about images means building in all these things that we've been working on for a long time, but it also means that you've got to be able to respond to new questions in real time. That's the interesting part of this process, right? Not that the typical deep vision process is you come up with a question, which is a real piece of engineering, right? You're trying to figure out what's going to be publishable and all this sort of stuff. You generate the right set of training data, which might take you some months. You mark up that data, which will take even more months. You come up with a method to answer the answer the question that you've come up with, and that's going to take you more months, and you get an answer, right? So you can, and it's a year later. It's a year since you asked the question, right? What's nice about the visual question answering process is that although you still have this crazy process of capturing training data and doing all the markup and all of that, you ask a question and you get an answer a second later. And that's important. All of these ideas about intelligence, right? Even just the Turing test, right? The Turing test isn't a great measure of intelligence, but even the Turing test requires a conversation. Right? You've got to answer the question that's put to you now, not answer the question that was put to you 12 months ago. Yeah. So one of the key factors of everybody's idea of what AI is, it's that you have to react in real time. And there is this great work on the visual Turing test. This is one of the images from the visual Turing test, and the question that goes with this image is there a person that is female in the designated region? And it's a really nice idea. They made some kind of compensation for the fact that a lot of these things aren't real time, but it's a really nice idea. Okay, so attributes for visual question answering, much the same idea. We're going to do the detections and try to figure out our attribute vector out of that image. We're going to put that information into an LSTM, but now that LSTM is going to take this question and try to generate an answer. And it has, as before, it has this great advantage that it now knows the kinds of things that people are interested in about this image. And this is just a representation of the fact that you can use the same process to do image captioning, single word question answering, and sentence question answering. So some examples. Here is an image. The top 5 attributes are couch sleeping, dog laying, and brown. And the questions are, does this animal appear to be resting? To which it gets the right answer, yes. And what's the colour of the cushions? And that's a pretty impressive result, I think. A bunch more examples. The best question here is this woman trying to give the kids an uncooked cake? Yeah, that's some pretty specific knowledge. But in reality, as soon as you see this kind of question, you've got a 50% chance anyway, right? The answer is going to be yes or no, so it's not really showing any great insight there. For this one, the best question is this one here. How many carrots are in the bowls? The answer to how many questions is pretty much always 2. After that, it's 3, closely followed by 1. Yeah? One of the big problems with this LSTM-driven process of answering these questions is that you can't tell, well, sorry, you can tell, but people tend not to look at whether the answer is just being picked out of the training data, right? Is 2 just the modal answer out of the training data? And in this case, it probably is, right? But I can guarantee that over 10, which is supposed to be the ground truth here, wasn't in the training data. We have not given this thing the capacity to learn the answer over 10. And again, when you add attributes to visual question answering, you get all the bold numbers in all the right places. So that is, but that is applied to those data sets, right? And I think those numbers were particularly the question answering data sets built on top of Microsoft Cocoa, which contain largely a really particular kind of question, which is something that you can answer out of the pixels relatively straightforwardly. I think that where we need to be going is towards much more interesting questions. So this is one I made up the other day. Did the player win the point? I think that it's relatively easy to see there that he's hit the ball into his side of the net, and therefore that he lost. But of course, you've got to have other information to be able to. You've got to have some information about tennis to be able to answer that question. If you ask the Visual QA bot from MIT, then the answers you get are yes, tennis court, and no in that order. No is the correct answer, but it really has no. It's an unfair question, right? It's not trained on that kind of data. So where was this photo taken? The answers that it gives are no, yes, and lake, none of which are true. And again, I'm not picking on Visual QA from MIT, right? This is a shortcoming in the data. It's not a shortcoming in the method. And who's winning, right? Yes, no, and skiing. I like the idea that skiing's the real winner here today. But I'm not sure that that's what it meant. So, and one that comes up, people ask, there are people interested in these kinds of questions. How many calories in this meal? And the answers are dessert, breakfast, and yes. And that, that's somebody's, if that's what people are eating for breakfast, we've got more to worry about. So, NLP question answering tackles harder questions, right? Watson won Jeopardy with this. The question was, William Wilkinson's An Account of the Principalities of Wallachia and Moldavia inspired this author's most famous novel. And the answer is Bram Stoker, right? But the Watson process, which is open architecture question answering, was able to go through its databases in the time that it had available and pull out that answer. We're a long way from that kind of question, right? So a visual version of that question might be, who wrote a book about this guy? And we're a long way from that question, right? Some of the Trek questions. So Trek has a great process where they provide a data set, so gigabytes of documents, which you then have to answer these questions out of. And so the questions for this particular one that I was looking at are, what was the monetary value of the Nobel Peace Prize in 1989? What does the Peugeot company manufacture? How much did Mercury spend on advertising in 1993? And the average performance apparently is about 70%. And we're a long way from answering questions like that about images, right? And the stuff they're doing, this is just one thing, and it's actually relatively old. This is one kind of architecture for answering these kind of questions. It's a complicated thing, right? They're going into these data sets and really examining them and finding ways to bring information together. So we need to be looking at questions where visual information is not enough, and that's kind of where we're trying to go, right? We're just making a step towards it. Don't think for a second that I believe that we've solved this problem at all. But one interesting question might be, how many mammals in this image? And we can answer this question, right? Dogs and cats are mammals, birds are not, is the kind of information that we need to be able to answer that question. The way that we're bringing in other information is to try to bring it out of a knowledge base. There's two ways that we're doing it. The first is to pretty much Google it, right? It's actually, we're just Googling it in Wikipedia. So you take the top 5 attributes that come out of your detection process, go into Wikipedia, get the text associated with those attributes, give that text to the RNN in order to make up its mind, and that adds information into this answering process. And it's pretty, it's pretty agricultural, but it still works, right? So you take the image, you put it through a CNN, the CNN goes around to the captioning process, and we generate 5 captions and put those through. The CNN activates, the feature goes through itself, and then up here we query DBpedia, which is just Wikipedia, get the relevant text out, put that through Doc2Vec, and put all of that into the LSTM, and the LSTM learns to use that information to answer questions, right? So now we've gone out to the web and got some information that's relevant, right? We know it's relevant because it's Googled out of the attributes. So here's an image, here are a bunch of attributes that come out of it, one of the 5 captions, some of the external knowledge, and the question is, why do they have umbrellas? And the answer that it gives is shade, and shade is visible in the external knowledge that's pulled out of Wikipedia. And it's all it's all just going into an RNN, so you don't really know what it's doing with it, but at least it's adding value, right? The bold numbers are in all the right places. Okay, and it answers questions that we'd ordinarily have trouble with, like why are the zebras in water, why is he swinging backwards to hit the ball, and there's a couple of, let me show you some failures, I'm running out of time, but there are some failures here. The top right one is what's on the keyboard, and the answer is mouse. The answer we give is mouse, whereas the truth is cat, and you can understand how that error might have been made. Okay, and it works better for some questions than others, and particularly works better. But the most interesting column is this little blue one at the end here, which are the why questions, right? And the why questions is the straightforward approach. Well, the straightforward approach really is kind of this one. No, which one is it? VGG and LSTM here. Gets about 4% of the why questions right, and we get about 14% of the why questions right. And the why questions are the ones that are closest to being interesting. And they're also the hardest ones to get right, because the why questions have the most open-ended answers. Now, we want to try to get better information in there. All we've got so far is text. What we want to do now is to be able to go into a knowledge base, right? I'm afraid I'm kind of running out of time, so I've got to go a bit faster. But the knowledge base is made up of RDF tuples. It lives in a DBMS, which does inference for us. It takes queries in SPARQL, right? Which is a lot like, so RDF is just a bunch of tuples, right? Obama, President, United States of America. But what's missing is everything, gravity, everything, right? It's not common sense, it's some really specific information. And you can query this thing in SPARQL. And it means that we might even be able to achieve reasoning, right? And those of you who've seen me talk before will know that I'm right into reasoning, right? So this is our one of our papers at CVPR last time, where we did some hardcore reasoning about 3D structural models in order to come up with a semantic answer. So what we do in this is we take the image, do our detections, get the attributes, then use those attributes. Each one of those attributes has a match in DBpedia. So you can then hook straight into DBpedia, right? So this diagram here, the things on the left are the things we've detected in the image, and they are linked through to these concepts in the database. And what that means is that we can ask this question of the, well, so that question before was how many mammals in the image, right? You can't have a mammal detector. But you can ask how many mammals are in the image, because this one has 2 giraffes, right? Because you've got object 1, which is a giraffe, which maps into Wikipedia, and you've got object 2, which is a giraffe, which maps into Wikipedia. Wikipedia, if you chain through it, tells you that a giraffe is a mammal, and so you can then answer this question: how many mammals in the image? And it gives you a reason, right? it tells you that that's how it's done it. So it's all dependent on this RDF data set, right? This knowledge base, and that's the weakest link in the process, right? That actually DBpedia contains such a tiny amount of information, most of which is not actually wrong, but encoded in some pretty strange ways, and some pretty critical stuff is missing. But nonetheless, we formed these are 23 question types that get transformed into SPARQL queries, which you can run on this DBMS, which means that you can actually do inference on the content of images, right? So some of the questions you can ask: list close relatives of this animal. And the answer is donkey, horse, mules, asinus, and hinny. Right? And it's found that by traversing the knowledge base. Which object in this image is most related to entertainment? The answer is TV, but the reason that it gives you is television, performing arts, entertainment. Right? It's a chain of reasoning through the data set. So list the common properties of these two images. It says they've both got grass in the background, and they contain these object concepts, which are livestock animals, domesticated animals, herbivorous animals, meat industry. Let me skip through a bit. List common properties of these two images. Scene concepts, transport infrastructure, right? You give it a train station and an airport, and it tells you that they're both transport infrastructure without... There's no features in common between these images, right? There's nothing visible between them that tells you that they have that similarity. It's going through the RDF database, it's going through the knowledge base that gives you the capacity to answer that question. And it's based on QP, not LSTMs. Obviously it doesn't do very well on the COCO questions, right? Because it's running this kind of process which is specifically tied down to DBpedia, and most of the COCO stuff isn't in DBpedia. But the major limitation, as I said, is that most of the stuff you want to know isn't in DBpedia. So we need to figure out how to get, a version of DBpedia which actually or a knowledge base, sorry, not a version of DBpedia, a knowledge base that has more of the information that we actually want to be able to use in image interpretation, including gravity. So the message is, well, there's a few messages there, but one of them is that we really need to think about representations if we're going to get anywhere with this bigger AI problem, that we should probably keep our eyes, open up a bit as a field to these bigger questions. But, this pendulum image is here because I'm hoping that this time we might not overcorrect to this process, right? That instead of overfitting to the neural network process and forgetting all of the analytics that we've done, we might be able to come back and do something in the middle and achieve something greater without overreacting to whatever comes next. That's it.